alternative protein. Please join me in welcoming Professor Elena Provernov from the, she is actually the head of the Advanced Materials and Agro Nanotechnology Research Center at the Agricultural Research Organization, the Vulcani Center. Please, Elena.
Yoram, thank you everyone. Just a moment, I will check how I. Can you hold me here? Yeah.
Use this one.
Yeah, and okay, okay, just like this. Okay, okay. Okay, this. Okay. Like this?
Yeah.
Okay. Okay, hello everyone and good evening. And today our project that started 3 years ago. This is actually the active biodegradable food packaging from bio waste of the alternative protein industry. And actually the participants of this project is our group, together with Professor Victor Rodov from Vulcani Institute, and our US collaborator is Professor Eva Elmenar Rosarini, and our industry partner is BASF Industry from Israel. Okay, so first of all, why package? Okay, why this project? Okay, actually the idea was to solve several problems in one shot. So we have a problem of the food loss. Okay, and we know that actually the food loss and package, you probably know it also in your home, that package can help very effectively to decrease the food losses, because it just protects the food from environmental damages, it reduces the escape of water, and so on and so forth. Okay, but on the other hand, we have the problem of plastic package. Okay, I think everyone is aware about the problem, so no one needs more explanation about it. We have like billion tons, trillion tons of pollution, okay? And in addition, so actually the idea was to do the package from biodegradable material, as again, this is not our idea. The idea is in the air. Okay, and actually here you can see how much food is wasted every day, every year in the global food waste. So indeed, package help, and we need package. But again, let's do it biodegradable. So, and what is, I think, quite special about the problem, this project is the compounds from that we decided to do our bio package. Okay. So actually, biodegradable package, we wanted to do it from chitosan. Again, chitosan is non-compound, but here we wanted to use chitosan that we take from the alternative protein industry. Actually, the alternative protein industry, they are looking for different sources of the proteins. And one of such sources is BSF. BSF, which is the black fly soldier. This is the insect that eats almost everything, and actually it can be a very good source for the alternative protein. Okay. But in addition to the protein, okay, this protein, for instance, in Western countries is mostly used for feeding animals, not for feeding people. Okay. But still, this is very important industry. And this industry has byproducts, chitin. Chitin is something that cannot be digested in our gastrointestinal system. So this is actually the byproduct, the waste, okay, something that they want to rid of. And we decided that we will use this chitin in order to get our biodegradable materials. Okay, I skip this row, the about regulatory aspect of, but BSF indeed is a good source. Okay, so actually it was like the combination of two projects. We joined the big NIFA project about the biodegradable food packages with our idea to use specific part of the valorization of polysaccharide-rich agricultural waste. Okay. Okay, the team. My group, okay, it's also the group of, and our group, our expertise is polysaccharides and biodegradable materials in general, okay? Also, my collaborator in Israel is Professor Victor Dodov, who is an expert in the post-harvest storage, okay, and packaging. And from the US, Professor Era Alminar from Michigan State University. She's actually the expert in packaging. She's the person from the packaging board. Okay? And as I told, the BASF, our industries, is our commercial partner who provide us with byproducts for our heating. And the most important, okay, the team who actually doing the work, these are students, okay? So here you can see the main person in this project is in Baldom, okay? She did the most of the work. And also Esther Wangi from Victor's group, she helped her, okay, to do all the microbiology experiments. And in addition, there are two, actually all the group helped to involve, but the mostly is Shizab, she's sitting here, okay, and Alex, my lab manager, who also helped to involve a lot, okay. And now, as you can see, it reminds the paper title. Indeed, now we are submitting paper about this project. Okay, so as we told, the idea was to prepare a series of different bioplastics with different properties in order to adjust the specific requirements of food products. So we wanted it also rigid, also flexible, how to do it from one product. Okay. So first of all, we wanted to take the residues of chitin and to yield from there our polysaccharide, our chitin. Then from chitin, we can do deacetylation in order to control the properties of materials. And the last objective was to use the materials that we will receive for biodegradable packaging. And here you can see methods, okay? So in order to, actually here, we use two methods, okay, for yielding of chitin. In one method, we use organic solvent, and in our methods, we use it only water, and we still got the chitin with the properties that are good enough and very comparable to the chitin without this organic salts. I mean, first of all, we found the greener matter for the second chitin. After that, we took the chitin and we performed deacetylation. And here we use some trick like cycling of freezing and heating, and we increase the yield and we increase the, okay, here how we determine our yield and degree of deacetylation. And here you can see that we got a series of different materials, okay, with different degree of deacetylation. And here you can see the TGA. This is actually the polymers that shows how exactly we got the material. Okay. And here you can see the solubility test. You see how different is it? And this is actually the effect of the deacetylation degree. And here, okay, we did the rheology in order to see the rheological properties of our materials. They are also very different. And here you can see the molecular weight. Also, it depends on the degree of acetylation, because degree of acetylation is actually controlled by the reaction time. Okay. So after that, we did a series of films. You can see the films. Okay. Some of them they are completely insoluble. Some of them they are mechanical properties more flexible. Some of them they are rigid. Okay. And you can see the films here. Okay. And also you can see that films, they change from in terms of their hydrophobicity. But all of them, they are relatively hydrophobic. It means they are resistant to water. Okay. And also you will see the mechanical properties. They depends on degree of the acetations. Here you can see the electron scanning microscope images. And here, the last part, actually we use this film in order to do package. in order to do package, and as a package, we do is a food model, we do fresh cut pumpkin. Why fresh cut? Because these products are very prone to microbial damages and also to the physiological damages. And it provides it's actually a good model that can show us if our packages they are good or not so. Okay, so here I would like to show you the color change. As I told, there are also some physiological changes, and we can see that our BSF chitosan provides the best preservation of the color. Something else, and this is, I think, the most important, you can see our BioSet, actually we compared it to the plastic package, okay? And we compared it to commercial chitosan, which is done from the crab shells and shrimp, okay? And our chitosan is done from this black fly salt. And we can see that it is known that chitosan has antimicrobial properties, but our chitosan provides much more efficient protection also from the bacterial damages and also from fungal and yeast damages. So this is something that was unusual and surprising and very interesting. I think that's it. We also check the structure and check the water loss. But what I want to conclude is that actually the degree of the acetylation, we can adjust this degree of the acetylation and it will customize the properties of our materials. And we see that this is quite good packaging, and it can be different applications in addition to packaging. Also, it can be for medical testing and so on and so forth. So here I would like to thank you. First of all, I would like to thank the BARD, thank NIFA and the Innovation Authority. I think it's wonderful initiative. We are very happy to do this project. And I would like to thank all my students and thank you for your listening. Thank you.
Thank you very much, Elena. Please, any questions? One question, please, from the audience here.
Yes.
Yes, please. Hi, everyone. Wait for the runner.
How that the BSF chitosan has a brown color? Can you get rid of the brown color?
You know, good. Yes, good question. It's once it becomes film because it's relatively low percent. It's not brown, but still it's yellowish a little bit. Can be okay. You can get it much whiter, but then you still need some organic solvents. But if you are okay with a little bit yellowish, the process is completely green because you just this a little bit of pigment that we still have. Yes, but maybe it's provide also some UV protection, so it can be also good.
Okay, thank you very much. Before you go, I would like to thank you very much for sharing with us the nice results. We see a lot of progress, a lot of array of application that might be from here. We decided to give you something. I don't know if you can see from far away. It's a nice bulb which just sprouted, meaning that the project start to sprout. Very soon it will bloom and it will be real, but we know that it requires a lot of work. So please, now BARD is providing you a
Thank
hat.
you. And one
Adjusting all the-
with my collaborator.
Yeah. Thank you very much.
Thank you. Thank you.
Okay.